Okay, so last time we talked about the derivative. Why did we talk about the derivative? Because the derivative allows you to go beyond describing how motion takes place in simple terms. Okay, so if you want to describe how motion is taking place, the very first thing that you'll do when you are measuring motion is to measure the position of an object. So right now we are focusing on an object that is traveling in one straight line. You measure the position of the object as time changes. So that's the very first thing you do. The tool of the derivative, as in differentiation, allows you to go beyond that. It allows you to answer the question how fast the object is moving, and then how fast is its speed changing. So how fast is it moving is of course captured by the speed or the velocity, and then how fast the speed is changing is captured by the acceleration. Okay, and basically the speed or the velocity, right now there's not really much of a distinction between speed and velocity. They become important when we talk about vectors, but for motion along one straight line they're basically the same thing, so I'll use them interchangeably for now. The speed and the velocity is defined then mathematically as the derivative of the position, and the acceleration is the derivative of the velocity. Okay, so these very basic quantities that you see in mechanics have to be written down in the language of derivatives. Okay, so that's why you have to become very comfortable with what we mean by a derivative. Okay, so if you define the speed, that is defined as dx by dt. If you look at the acceleration, that is defined as dv by dt. Okay, and so it's worthwhile to just take a pause and just look at this notion of differentiation or taking a derivative more carefully. That's essentially what we started to do last time. The idea, remember, is that you have to calculate a rate of change. So given a function, any arbitrary function, you have to look at the rate of change of this function. So to calculate the rate of change at any particular point, if I'm looking at the rate of change at that point, to begin with, that question doesn't even make sense, because how can you calculate the rate of change at a point? Because you have to consider a change. You have to consider 2 points. Okay, so where should the second point be if you're just talking about a single point? The idea is that you do consider a second point, but you make it closer and you investigate what happens when you make this second point come closer and closer to the first point. And then you look at the rate of change using these 2 points. That's the basic idea. Graphically, that just means that you have x and you have f of x and you have some function. By the way, ये जब आप fill करते हो मेरे पास time login हो जाता है, तो आप करने की ज़हमत ना करो तो बेहतर है वैसे. I will know that you did it at, somebody did it at 8 p.m. Okay, so thank you very much. Okay, so anyway, so you have 2 points on this graph. If you are looking at to calculate the rate of change at this point, say this has x coordinate x, and of course the value of the function at this point is f of x. You consider a second point that has coordinates x plus delta x being the difference in the x coordinate between the 2 points. So this second point has coordinates x plus delta x and then f of x plus delta x. These are the coordinates of the second point. So you essentially are going to draw a straight line that joins these 2 points, and you look at the slope of that straight line. That essentially gives you a rough estimate of what the rate of change at this point is going to be. This answer, of course, depends on where you choose the yellow point to be. Okay, so if you choose it to be over here, then you get a different answer. If you choose it to be over here, you get a different answer. But if you're going to look at the rate of change at this point, this yellow point better be very, very close to this white point, because you're looking at the rate of change at that point. And basically you then look at what happens to the slope of the straight line that joins these 2 points as you make the yellow point come closer and closer to the white point. Okay. Now I will assume, since you are taking a concurrent course in computer science, and I also was involved in your admissions, and I read lots of admission files, and basically every second person had written in their personal statement that I've been interested in computers since I was 4 years old. So forgive me if I do put in some programming in this course, since you have been doing it since 4 years old. Okay. So basically what I'll be doing as far as programming is concerned is the following. You basically, let me open a new window, okay. Let me do it in incognito so that you basically get the same display as I do, okay. Okay, so you go to this website trinket.io. Don't do it right now. The advantage of Trinket is that you don't need to install anything to run programs. Okay, so you go to this website, you sign in, which I've already done. So of course you will have to make an account on this website. It's free, or you just use your Google account. Either will do. Okay, so once you make your account, you can essentially go to your programs. You can write these little programs, which are called trinkets over here. Anyway, these are snippets of code essentially. And you can write all kinds of different programs over here. Let me just open this program, the derivative program that I've labeled as a derivative. Okay, let me just zoom into this, and we can go through this, what this program is doing. Essentially, this is calculating the slope of the line that joins 2 points on the graph of a function. That's essentially what it's doing. Okay. This first line is something that you see in every program. Essentially, I'm going to be using Visual Python. So this first line, it just tells it that what is being used is Visual Python version 3.2. You don't need to worry about that. That number 3.2 might change in the future. Okay, so that's not really important. Whenever you try to write a new program, this will essentially automatically generate. This xmin and xmax, by the way, this hash thing tells it that this is a comment. This hash thing is basically explaining the program. These green colored lines are all comments which are explaining the program. Xmin is basically 0, xmax is 2.1. This is basically telling it the values of x over which to plot the graph. You're going to plot the graph of the function from x is equal to 0 to x is equal to 2.1. Basically setting up your graph paper, the extent of your graph paper. Okay. X naught is basically the value of x at which I'm going to calculate the derivative. Okay. Over here it's 1, it could be some other point. Okay. Delta x is basically the delta x that you're considering over here. Over here I set it to a very small value. Let us set it to a bigger value. Let us set it to 0.5 to begin with. Small step x is another change in x. That's just to plot the graph. Because essentially a computer cannot calculate the function at every point. It has to essentially calculate the function at discrete number of points because it has a finite memory, and then it just draws a smooth curve through those. Okay, sure. I can zoom it some more. There you go. अब नजर आ रहा है? I forget कि इतना gap भी है initially. Okay. Okay. अब ठीक है? Okay. Lines 14 and 15 essentially specify that you are going to plot two curves, one in color blue, one in color red. Don't worry about the syntax. Okay. In none of your exams, I'll ask you to write a program. Okay. But it's very useful for your own understanding if you learn this. Okay. How to write simple programs in this course, how to run simple programs, because that's really how you'll understand in many ways the different ideas in this course. Okay. This is basically the definition of the function. Line 19 and line 20 is where I'm defining the function. So I'm looking at the function f of x is equal to x squared. Okay. So what this function is doing is that you are giving it the name f, is taking in the number x, is throwing back the number x squared. Power in Visual Python is denoted by double asterisks. Okay. Single asterisk is multiplication. Okay. So once you have that, then I need to look at the slope of the line that joins the 2 points. That's obviously that. You have essentially doing f of x naught plus delta x minus f of x naught divided by delta x. And then you have to calculate the y-intercept of this line. How will we do this? Well, the line that is joining this point and this point is passing through the point x comma f of x. Right? So you can use this to deduce the y-intercept of this line. How will we do that? So you write down, okay, it's passing through f of x naught. So over here, just to be consistent with what I'm doing in the program, this is x naught, this is x naught, this is x naught, this is x naught. So f of x naught equals the gradient of the line times x naught plus the y-intercept. See, so what's the y-intercept of this line? f of x naught minus mx naught. That's exactly what I'm doing in line 26 over there.
Isn't this for a straight line?
Yeah. So I'm drawing a straight line between the 2 points. The slope of that straight line is giving me the value of the derivative approximately. Approximately because this is for finite delta x. Delta x को मैं छोटा करता जाऊंगा, then I'll see what happens to the slope. The smaller delta x I use, the more accurate value of the derivative I'll get. Okay? Right? Now you start, essentially you start from the smallest value of x, and now you are going to essentially keep on changing the value of x and see what happens. You're going to plot the function. What this does, this line 39 does is say that on the graph paper, put in the point with coordinates x, f of x. Line 40, put on the same graph paper, put in the points with coordinates x and the straight line x, essentially calculate mx plus k. Either mera y intercept k hai. Line 31, line 30. Okay. Once you have that, then you can just run the program. Let's run it. By the way, x is equal to 1 by my slope. I'm calculating the slope at x is equal to 1. So what answer do you expect for the slope of the straight line? X square hai function. X square, the derivative of x square is 2x. So at x is equal to 1, what's the slope? 2. So you expect the answer to be 2. Okay. Now I need to make this, of course, results udhar aayenge, so let me make it smaller to begin with, and now you just click run. Ye code aapka hoga. In excruciating detail, I provide you with this code, okay, and also a short document that explains how do you set it up, okay, किस website जाना है, किस तरह sign in करना है, screenshots लेके arrows भी बने होंगे like Dumbos, okay, कि click here, okay. So if you are saying कि भाई मैं तो I've always wanted to be a computer scientist, but I've never written down any program. That's the same as I want to be a zookeeper, but I have never petted a monkey. You can. This is a start, okay. Anyway, let's run it. And first time round it takes some time. So basically, you see this red line is the straight line that's joining the points with coordinates x is equal to 1 and x is equal to 1.5. Why 1.5? Because I set in my program delta x is equal to 0.5. So it's joining the points with coordinates x and x plus delta x. Okay? And the value of the derivative is approximately, it's calculated that to be 2.5. Not 2. Why not 2? Because delta x is not small. As I bring delta x closer and closer and closer to 0, this value will approach 2. That's exactly what we mean by the idea of a limit. What happens to this thing as we approach delta x equal to 0. Okay, so let's make this even smaller. That's the advantage of playing with the program. Okay, imagine doing this by yourself on a graph paper. You have to draw all kinds of lines. Let's make it 0.2. And now you see this red curve is essentially red line is now slightly different, and now the slope is 2.2. Now you make it even smaller. Let's make it 0.01. और वो जो आपने A level, FSC, O level की बुक में additional maths की बुक में रट्टा मारते हो कि it becomes a tangent line. Now you can kind of actually see it in practice. As I make delta x smaller and smaller, this will literally become a tangent line. So let me make it 0.01. And there you go. Now it's 2.01, and you can see the red line seems to be now really brushing the blue curve. Make it even smaller. That's the advantage of this. And by the way, you can run this on your mobile phone. So if you're in the washroom, this is something productive to do. Okay. Right? ये अस्तगफिरुल्लाह किसने कहा था? Okay. I mean, unless calculus has some religious connotations for you, I don't really think that there's anything wrong with that. But anyway, the slope of the straight line is 2.0001. Now, see, the closer, you're literally seeing the idea of a limit come into play right in front of your eyes. That's what I'm saying, okay. If you are able to write such a program by yourself, then you really understand what is meant by derivative. Okay. In this course, you learn things by doing, not by seeing me or listening to me, okay, or watching YouTube videos, or watching or listening to your friend explain wrong things, okay. You learn by doing things yourself. Okay, let's make it even smaller. So the next thing that we have to do is to explain to you that the derivative indirectly is telling you something else as well. If you know the slope, if you know how fast a function is changing at a particular point, or aka you know the speed of the object, practically speaking, you kind of know how much distance the object traveled in a small time interval as well. That's precisely how, for example, your car can tell you how much distance you traveled when you go from point A to point B. Okay. How is it able to do that? Well, essentially, if you have a function, just look at this, it's already there. Around the point x is equal to 1, the function is very well approximated, is being very well approximated by this red line. If you look at points close to x is equal to 1, which in this case is just because that's the point at which I'm bothering to draw essentially this tangent line, around in the neighborhood of x is equal to 1, I can forget about the blue curve. I can just consider the red line. Okay. And how do I calculate the change in the value of the function if I just consider the red line? Well, the red line is a straight line. I can just do slope of the red line times the change in the value of x. That gives me the change in the value of the function, aka delta y over delta x is equal to the slope, and therefore delta y is equal to the slope times delta x. That's all I'm doing. Okay. In other words, if you know the value of the derivative at a point, so by the way, the value of a derivative at a point has different notations. This is a function in general. If you want to specify that, okay, I'm going to calculate this function at a particular point, you write this, for example, that I'm going to calculate the value of this derivative function at x is equal to x naught. This is just notation. I'm just explaining, different ways of writing down the same thing. Many people just for simplicity write down this, that I'm going to calculate the value of this function at x naught. It's the same thing, of course. You also write down f prime x naught. F prime, remember, denotes the first derivative, and this thing just means calculate the value of the first derivative at x is equal to x naught. These three things mean exactly the same thing. Okay. Right? But remember that these three are now numbers. They are not functions. Okay? Right? Okay, now suppose I know the value of the derivative at a particular point. So then I know that f prime x naught, I know this. And you've already seen that this is approximately equal to, and I'll explain why approximately, this is approximately equal to this thing. That's exactly how I approximately calculated the value of the derivative just now. I'm saying approximately because this derivative, of course, this number is only true when delta x is very, very small. Over here, delta x is small, but it's certainly not going to be infinitesimally small. But for small enough delta x, this is approximately true. Okay, as you saw in the program. For delta x is equal to 0.001, we were getting that the value of the derivative was not exactly equal to 2, but this thing was 2.0001. Okay, so it's approximately true. That's why I'm writing these two squiggly lines, okay? Okay? Right? And then you can write this as delta f over delta x. The change in the value of the function divided by change in x. Just what I told you graphically. You are essentially replacing the curve around a point by a straight line. And so the change in the value of the function is nothing other than the slope at x naught times delta x, which you can also write as that. एक सेकेंड okay, ठीक है, okay, fine. इसको रहने दो, this is fine. हाँ बताओ, now what?
This last part, delta f is equal to
All I did was just that this is the change in the value of the function, which I've written as delta f divided by delta x, and all I've done is just take this delta x to the other side. Okay, so this thing is I should be writing this as approximately that. Okay, so the change in the value of a function is equal to the slope of the function at a point times the change in the value of x. Okay, in other words, if I say that you're moving with a speed of 60 kilometers per hour, what's the distance you have traveled in 1 second? It's approximately speed multiplied by time. Okay, but that is only approximately. If I say what's the distance traveled by you in a time interval of 0.0001 seconds, then even though your speed may be changing, but for such a small interval of time, your speed is approximately constant. Okay, so you can still do distance is equal to speed multiplied by time. Okay, rate of change of distance multiplied by the time interval gives you the change in distance. That's one particular example of this thing. Okay, right? Okay, so much for that. In the readings I'll upload, you'll see this in different contexts. Okay, this is something that we'll be doing quite a lot. So remember, the derivative does not just tell you the rate of change. You can use the rate of change to give you the change. Okay?
Sir, agar delta x, for example, when we are trying to find the derivative is velocity and delta f would then be distance and then delta x is time.
Yeah.
Delta f ढूंढना चाह रहे हैं, तो would it delta x also be 0 if it is supposed to if it is infinitesimally small?
No, it won't be exactly 0. It will be a very small number, but won't be exactly 0.
Find delta f.
It will be a very small number. उसके तरफ आते हैं. Okay. Right. Okay, so that much is done. Okay, now so hopefully now you have a much better idea of what a derivative is telling you. Again, I would like to emphasize that really our emphasis won't be on calculating complicated derivatives. It will be more on how to use derivatives. Okay, so what we have done is that if you measure position, you can calculate the velocity and you can then calculate the acceleration. This is what you will do experimentally most of the time. If you are studying the motion of an object, you note down its position, how its position changes with time. From that you measure its velocity, from that you measure its acceleration. The whole theoretical framework of mechanics works the other way around. The whole theoretical framework of mechanics goes the other way around. The whole theoretical framework of mechanics says that essentially figure out the forces acting on your object. Given the forces, you can figure out the acceleration, and if you are given the acceleration, you can then figure out the velocity, and then given the velocity, figure out the position. So it goes in exactly the opposite way with some additional ingredients. Of course, the additional ingredients being forces, which we'll talk about later. Okay, so right now I'm just describing how motion takes place. Forces come into play when we start to think about why motion takes place. Okay. So right now we don't need to worry about forces, we are just going to draw the link, the reverse link, that how do you go from acceleration to the velocity, and how do you go from the velocity to the position. Okay, so that's the central aim, the central question that we aim to answer today. Okay, how do you go the reverse way around? That's essentially all there is to describing how motion takes place. Okay.
Sir,
Yes.
I don't get this point, the reversal part, that why we need to go in reversal and why it helps to find motion.
Why it helps you find motion? Yeah. Because if you are given the forces, you cannot figure out the position. But you can figure out is the acceleration. And once you figure out the acceleration, then, because the acceleration is a starting point, is the central quantity that you find from the forces. F is equal to ma. From F is equal to ma, you figure out the acceleration. Okay. Then from the acceleration, you can then figure out the velocity, and then you figure out the position. Okay. So the question This reverse question is important enough that you can approach it in two different directions, which of course gives you the same answer, which of course are actually equivalent. Okay? So there are two different ways of looking at the problem. Okay? The first way is that, for example, you have this, and I say figure out x. So the thing that you want is trapped inside a derivative. Okay? And you have to extract it from inside this derivative. This is an equation in which the thing that you want is trapped inside a derivative. Such an equation is called a differential equation. It's not an algebraic equation. An algebraic equation would be something like x square minus x is equal to 1, for example. For solving such algebraic equations, there are straightforward ways to do it. There are very, very algorithmic ways of doing it. You just apply the quadratic formula, for example, in this case, out pops the answer. Solving differential equations is relatively more complicated. There's a bit of an art to them. So when it comes to solving differential equations, many times you have to guess the solution and see whether it works. Okay? There are less number of systematic, straightforward ways of doing it. Okay, so in this case, to make progress, I need to essentially know what v is, what this function v is. Is it constant? Is the object moving at constant speed? If its speed is changing, how is it changing? I need to know that before I can figure out x. So to begin with, let's assume that it's moving with constant speed. Then how do I figure out x? Well, the time-honored way of doing this is to stare at it and guess the answer and see whether your guess works. If it doesn't, you modify your guess until it works. That's basically the way to do it. So basically, so this is a constant. So basically, you're looking to write down some function such that when you differentiate it, you get this constant v. So our first guess is t. It's not t square, because if you differentiate t square, you get something proportional to t. That's not a constant. It's not going to be t cube, because you get 3t square. That's not a constant either. It's not going to be e raised to pi t, because you differentiate e raised to pi t, you don't get a constant. You don't get a number, a fixed number. It's not going to be sine of t, you don't get a fixed number. You get a number that keeps on going up and down and up and down. Okay? So the first guess is t, because if you differentiate it well, at least you get 1. Okay? That's well and good, but you're not getting v. This is also wrong on another front, is that you always must remember that you're doing physics, not algebra or not calculus, just calculus, plain old calculus. You're doing physics, okay? So everything you have to always ask yourself, how will I measure something? In what units will I measure it? This has units of position. This does not have units of meter second. This is not position multiplied by time. This is position as a function of time. As in, I'm looking at how does the position of the object change as time changes. So the left hand side has dimensions of meters. The right hand side right now has dimensions of time. Okay? In SI units, that would be seconds. Okay, so you cannot have, this cannot be true. Okay, and it's obvious just from dimensions, I need to multiply this t with something that has dimensions of speed in order to get something that has dimensions of distance. And the only speed that I have right now is this v. So the thing that I should be multiplying this with is v. Another way to see that, of course, is that if I differentiate this, v is constant, remember. If v was not constant, then the derivative of vt is not simply v. If v is not constant, then it's something else, of course, a derivative. Okay? So this only works when v is constant. But that's not the only answer that I can write down. I can always add in a constant. This also works. If you differentiate this thing, when you have a sum, you want to take its derivative, you essentially calculate the sum of the derivatives. So the derivative of this sum is the derivative of this thing plus the derivative of this thing. The derivative of this thing is 0, because this is a constant. As in, the graph of this thing is a horizontal straight line. What's the slope of a horizontal straight line? 0. Okay? So the derivative of this thing is 0 and the derivative of this thing is v. So yes, this is a mathematical solution to the problem of solving this differential equation for the case where v is constant. But since you are doing physics, you run into one big problem straight away. Any symbol that you write down, any variable that you write down, you need to answer one basic question. What does it mean? That's another fancy way of saying, how do I measure it? Since you are doing physics, every symbol that you write down, you should come up with, at least in principle, a way, a method to measure it. How do I measure C? That gives me some idea about what C is physically. Well, what's C? Yeah, so you put in t is equal to 0, and you get from this mathematical function, you get x t is equal to 0 gives me v times 0 plus c. This of course is 0. This is not v of 0, this is v multiplied by 0. So again, it seems trivial right now, but a huge source of misunderstanding is always, you have to consider, okay, is this the input to the function, or is this just a multiplication? This is just multiplication, v multiplied by 0 plus c. So this is just c, aka c is just equal to the position at time is equal to 0. In other words, this is the position of the object at the instant when I started my clock. And it's up to me to start my clock.
Sir, can you just explain to me how you made the equation at the bottom? Yeah, this one, how you made it.
Okay. You are looking to write down some function such that when you differentiate it, you get v. So if you just write down t, you get 1. So you have to multiply t with v. So if you take the derivative of this thing, you just get v. Okay, but that's not the only solution. You can always add in a constant. You take the derivative of this thing, you get v. So that is the solution. Okay, essentially it's a solution by trial and error. Okay, that's basically the logic. There's a theorem in differential equation that says that for simple differential equations, the solution is unique. So once you have found a solution, you have found the solution. Okay, just like if you have a quadratic equation, if you manage by trial and error to find out 2 roots of the quadratic equation, that's it. The quadratic equation only has 2 roots. You don't need to go about searching for a third root. Okay,
Sir, in finding this equation, can you just integrate the differential?
Yeah, I'm coming to that. Okay, essentially it's the same thing. Okay, right. So this process of essentially looking for a function whose derivative is something is known as anti-differentiation. You're kind of doing the reverse of differentiation. So if you have a function f of x and I say find out the antiderivative of this function, that means that I'm going to find out capital F of x such that if I differentiate capital F, I get the original function. That's what I mean by the antiderivative. The antiderivative of a function is another function such that when I differentiate this new function, I get back the original function. That's essentially what I did over here. X is the antiderivative of v. I differentiate x, I get v. Okay. V constant है. When you take the derivative of this thing, when you take this derivative of this thing, v pops out of the derivative. You're just left with the derivative of t, but that derivative is 1. So you just get v times 1, which is just v. Okay. Or another way to see this is that this is a straight line with gradient v. इसकी slope क्या होगी? V. Okay. Okay. So what we have found is that this is true for constant v. This, by the way, is absolutely nothing new. This is something that you do in grade 6, grade 7. Speed, distance is equal to speed multiplied by time. This is a grown up version of that. The only difference, of course, is that you're also seeing this x naught. Now, why are you seeing x naught? Why didn't you see this in grade 6 and grade 7? Yeah, so basically in grade 6 and 7 you essentially it's up to you where you up to you to set the point from which you measure positions. If you can set the origin of your coordinate system, the point from which you measure positions, to be the same position at which the object was at the instant when you started your clock, x naught is going to be 0, because the object is at the position from which you are measuring position at the instant when you started your clock. Okay. But in general you do need this x naught. Why? Because suppose you are considering the motion of two objects. One car is going like that, the other car is coming like that. Say both of them are moving with constant speed. For at the instant when I start my clock, I can set the origin to be at the location of one of these cars. So I can make x naught to be 0 for one of these cars. But for the other car, x naught won't be 0. Okay. So you do need this x naught when you are dealing with the simultaneous motion of more than one object. In grade 6 and 7, of course, you were still young enough that you didn't need to bother about the motion of more than one object, so you were happy without x naught. Implicitly, x naught was being set equal to 0, so you didn't need to worry about that. Okay. But now you do need to worry. Okay. Right. Of course, this was for a very simple case in which the velocity was constant. Now let's deal with the case where the acceleration is constant. And of course, this is something that this is a case that you just love, all of you. So you have A is equal to dv by dt. And if again I say that A is constant, give me this function v. Well, mathematically it's exactly the same problem as before. Look, previously my problem was v is equal to dx by dt, and the solution for this that I found was x of t is equal to v times t plus a constant for constant v. Mathematically this is exactly the same problem for constant a, because all I have done is to replace v with a, replace x with v. Physically they are different, of course, but mathematically these are just the same. They are basically the same mathematical variable has been given different names. So I can just straight away write down the solution. Wherever I see v, I just write a. Wherever I see x, I just write v. So v of t is equal to at plus a constant. This constant, of course, will not be the same as that constant, but for the sake of simplicity, I am using the same symbol. But of course, it's not the same constant. Okay. Now, again, I need to give this c, this constant, some physical meaning. How do I do that? You put t is equal to 0. So v t is equal to 0 is equal to a times 0 plus c, which is just c. So c is nothing other than the velocity of the object at the instant when you started your clock. Okay, so this is a very, very common confusion. Oh sir, you threw this chalk up in the air. Okay, how is the initial speed 5 meters per second? Well, I started my clock just after this chalk left my hand. That is t is equal to 0 for me. Why are you worried about what the chalk was doing in my hand? Okay, that's not what you need to analyze. To analyze what the chalk was doing in my hand, how exactly I threw it, I need to look at the force that my hand exerted on this chalk. But the end result of that force is that the speed of the chalk just after I threw it is 5 meters per second, for example. Okay, so this instant when you start your clock is very important. It seems something very basic and very easy to understand. This is a very common source of confusion. Okay, always worry about what exactly is the instant when I started my clock. Okay, right, and different objects can start moving at different times. So I throw up some object at the top of an adjacent tower. My friend throws down an object 5 seconds later. You need to take these 5 seconds into account in your mathematical framework, because both objects did not start moving at the same instant of time. Okay, so this when you start your clock is very important. It's not as trivial as it may seem. Anyway, so typically this symbol v t is equal to 0 is given a special symbol u, and so this becomes one of the first equation of kinematics, one of the more pompous names that you'll hear, okay, according to you. I never call it that. This is extremely simple, you know, anti-differentiation right now. You can also consider it to be an integral, as you'll see. An integration is something else to begin with, so I'm not using the same name as anti-differentiation. But it turns out that mathematically, it turns out that it is the same thing, but it's not obvious to begin with, okay. Anyway, so V of t is equal to u plus at. This is only true for constant acceleration. I emphasize that again and again. After this whole course, if I give this problem, in which you have a spring, you have a block, I hit this block with a hammer that gives the block a speed of 2 meters per second. I say what is its speed after 0.5 seconds? V is equal to u plus at. That doesn't apply in this case. The spring exerts a variable force on the block. The force that the spring exerts on the block keeps on changing, and therefore the acceleration of the block keeps on changing, and therefore this thing does not apply. The whole notion of work and energy was made, energy came into being literally, historically speaking, to handle the situation of the force not being constant, aka the acceleration not being constant. But of course, you bypass all that and said that my acceleration is always constant in my way, therefore V is equal to u plus at, okay. Okay, so don't make the same mistake, okay. Given this, of course, I can go one step further and say, well, what is x then? If V is of this form, what is x? V is equal to dx by dt. I need to write down a function x such that when I differentiate this, I get not just a constant V, I get u plus at. So this is a slightly more complicated problem, slightly. So I need to cook up a function x such that when I differentiate, I get this thing. Well, let's just do it by pieces, okay. What do I differentiate such that I get u? U is a constant. Why is it a constant? U is the initial speed of the object. Is the speed of the object at the instant when I started my clock. Once I note down that speed of the object is not going to change. That speed of the object, the initial speed, the speed at the instant when I started my clock. No matter what the object does in the future, that speed is fixed. Okay, so what do I write down? Ut, easy, right? You differentiate this, out pops u, derivative of t is 1, so just left with u. What do I differentiate to get at? You don't need to get the correct answer straight away. That's a very important point, okay. A lot of this science and mathematics is done by trial and error. It's okay to be wrong as long as you realize that you are wrong. Okay. Many of you give me a solution that contains anti-gravity. Things instead of falling down escape to space. But then you have the gall to actually write QED after that, okay. And that gives me a great motivation to actually subtract further 5 marks, okay. Okay, at least if you made an obvious error, at least own up to it, okay, rather than deal with it, sir, okay, yeah. Okay. So, your first guess will be, I need something that contains t. The first obvious candidate is, of course, t square, because if you differentiate t square, you get 2t. Okay. The only problem with this, of course, is again, that this has dimensions of time squared. This has dimensions, of course, of position. What physical quantity can I multiply with t square to get dimensions of position? Acceleration, of course. That's exactly what is over there anyway. Now if you differentiate this, you get 2at. This is extra factor of 2. Well, it's easy enough to get rid of that. There you go. Now you differentiate that, you get at. That's what I meant, okay. You cook up a guess, see if it works. If it doesn't, modify your guess. Okay. It's very straightforward. Plus, of course, you need a constant. Again, this is not the same as the previous constants, but I'm using the same symbol. Okay, what is the physical meaning of this constant? Again, put in t is equal to 0. You get u times 0 plus half times a times 0 squared plus c. And that means that c is just the initial position. The position of the object at the instant when you started your clock. Again, depending on where you place the origin of your coordinate system, aka depending on which point you started measuring positions, this can be 0, this can be non-zero. So you have that. the acceleration is constant, because this is only true when the acceleration is constant. Okay. Now of course there is a third equation of kinematics, okay, or third equation of motion, which depending on which school you went to, or more importantly which academy you went to, is v square is equal to u square plus 2ax, or v square equals u square plus 2as. Okay. Both of those are wrong, by the way. They're slightly wrong, they're slightly incomplete, as you'll see. Okay. You can derive that, by the way, from these equations simply by eliminating t from here. So you can do t is equal to v minus u divided by a, plug this thing all the way over here. Either we plug in karo, do some algebraic simplifications, and you'll stumble upon v square is equal to u square plus 2a times x minus x naught, not just x. Okay. We'll derive that in another way very soon, so that's why I'm not bothering with that derivation. But the important point to note over here is that when you're looking at that equation, you're looking at the dependence of v on position rather than dependence of v on time. Okay, so if you're given where the object is and you just want to figure out its position, it may be more relevant to apply v square is equal to u square plus 2a, x minus x naught. Okay. Okay, so far so good. Now I want to approach exactly the same problem in another way. Okay, which is essentially goes back down to delta f is equal to f prime x naught times delta x. The other approach builds up on this seemingly very, very simple equation. This thing is saying that, okay, to calculate the change in some quantity, provided that delta x is small, you can multiply by the derivative by delta x. But the important thing is that delta x should be small. That gives you a big hint. If you have say velocity multiplied by time, and say this is some complicated function, right? This is you driving a car, okay, for example, and you basically want to look at find out the distance that your car moves between this time, let's call it ti, and let's call this tf. You want to find out the distance. Okay. Now this, of course, you cannot think about calculating antiderivative straight away, because you don't really know the analytical form. You don't really have an equation for v of t, which you can then think about, okay, what do I differentiate so that I get this function? But there's another way to think about this. Okay. The change in a function equals the derivative times the change in the input argument, right? So if I look at this, if I say I'm looking at the change in the position, I can calculate the change in the position of an object by looking at the derivative of position multiplied by delta t in that case. Okay, so in other words, what I can do is this profound step. I chop this up into small pieces. Given a time interval, let me do it over here. Given a time interval from ti to tf, I can chop up the time interval into small pieces. In my head, of course, not कि आपको हथौड़ी नहीं मारनी, don't hammer down a clock or something. Okay, in your mind you have a big time slice. You're chopping it up into small time slices. Why you are doing that is because essentially you're going to do this, and this is only true when this thing is small. Okay. So if you then look at one particular time slice, say the jth time slice, depends on the number of time slices. If you have 100 time slices, suppose we look at the 47th time slice, it doesn't really matter. Okay. What's the distance moved during this time slice? How do I write that down? Forget about area. This is just the velocity, the speed of the object for this time interval multiplied by the length of this time interval. The idea being, you can look at that, or alternatively, you can say that, okay, since the time interval is so small, the speed of the object is approximately constant because the time interval is so small. During that time interval, during that very short time interval, the speed of the object just does not have enough of a chance to really appreciably change. So the speed of the object during that very short time interval is approximately constant, and therefore I can go back to grade 6 and just say that the distance moved during this very short time interval is simply the speed of the object for this short time interval multiplied by the length of this time interval. In equations, that means that the distance moved during this time interval is the speed for this time interval, which we write like that. This just means the speed of the object at time t subscript j, time at for the jth segment, okay, times delta t j. This is the length of this time interval. This is delta x j. अगर आप गौर से देखो, this is essentially in that notation, this is delta f is equal to the derivative of f times delta x. ये वही चीज है, v remember is the derivative of x. This is just a physical application of what you did over there. Okay, right? Yes, essentially yes. Okay, so now if you go back to this and say that you have divided this up into small species, you can see that this number v of tj times delta tj, agar ye tj hai aapka, what is v of tj? The height of this thing. This is v of tj. What is delta tj? The thickness of this thing. So what's the product equal to? The product is the area of this rectangle that you have formed. Okay, I am sure ये आपने phrase जरूर सुनी होगी, the area under the speed time curve equals the distance travelled. Why is that true even if the speed is changing? That's why it's true, it turns out. Okay, you chop up your big interval into small slices, and then you calculate the distance travelled for each slice, and then what you are going to do? You're going to add it all up. You add up all these little intervals to get the total distance travelled. If you have a staircase with unequal stairs, to make it more complicated, okay, how can you calculate the height that I've gone up? One way is of course that I measure the total height. कहीं side से जाके या कोई come up with a scheme to measure the total height. But and the smarter way would be to calculate the height, to measure the height of each stair, and then add it all up. That's essentially what I'm doing over here. I've chopped up the big time interval into small slices, calculated the distance, written down the distance traveled during one time slice, each time slice actually, and then I'm going to add it all up. So the total distance traveled will be what? V of t1 times delta t1. The distance travelled during the first time slice, v of t2 times delta t2. The distance travelled during the second time slice, v of t3 times delta t3. Distance travelled during the third time slice. Yes?
Sir, you said that the distance that's covered, that delta x, is approximately equal to v times, is approximately correct.
Yeah.
It's approximate.
It's approximate. In the limit where delta t becomes very, very small, but not exactly 0, then this becomes equation.
But if you make the interval smaller and smaller.
Yeah, so you get smaller and smaller numbers. But in the sum, the number of terms also goes up. The number of terms in your sum will also go up.
But then doesn't that mean the small error that's still there is.
Yeah, that's the job of your calculus course, to show that error goes to 0 as you make delta t smaller and smaller. You can prove it mathematically, rigorously, that the error goes to 0. Okay? I can justify it over here by showing you some pictures that it does go to 0, but you can prove it very rigorously mathematically that it does go to 0, provided that delta t goes to 0. Okay? Yeah, there was a big historical worry, precisely that. Okay, that maybe the error also blows up because the number of terms blows up and maybe the error in each term is still there, so the error goes up. Yeah, I get the point. Okay, but the error in each term falls faster. then the how the number of terms blows up. Okay, so you have that plus blah 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 v of t n delta t n. Capital N is the number of segments. Okay, so I have done what one of your life coaches probably told you, that if you have a complicated problem, divide into smaller and smaller problems, solve each smaller problem, and then think about what happens. I will literally take this to the logical absolute extreme. Capital N को मैं infinity करूँगा. So I've literally chopped up the problem into infinitely many small problems. This is a distance traveled during the first time interval, second, third, and so on all the way, of course, Now you may not believe it, but physicists and especially mathematicians are extremely lazy people. We only lift our hand when actually somebody forces us to, okay? So we invent all kinds of notation so that we have to write as little as possible. We are not fond of writing equations that are 1 page long. So there's mathematical notation that simplifies the writing of this. This is not really anything new. So all I'm doing is to write this in a short way. Okay. What is done is that you look up the Greek dictionary and you find a symbol that you like. In this case, the symbol that mathematicians liked in this case was the sigma. Okay, so once you have found an appropriate Greek symbol, you use that symbol. So let me just write it down and you'll see what I mean. This is just shorthand for that. And you can see, how much effort is saved just by writing this instead of that. How this works is that, first of all, sigma is meant to denote a sum. Okay, so that's what this symbol means mathematically. This tells it that, okay, whatever follows this symbol, first of all, put in j is equal to 1 in that. So first of all, put j is equal to 1, you get v of t1 times delta t1. Then put j is equal to 2. In between each thing that you are writing down, put a plus sign because you have a sum. So when you have this, you'll first put in j is equal to 1, you'll get this. Put in a plus, then put j is equal to 2. You get v of t2 times delta t2. Put a plus. Put in j is equal to 3. Keep on doing this until you reach j is equal to n. Okay? Now, of course, you'll be objecting, there's still some error. You need, because the distance traveled is only equal for a short time interval, the distance traveled is only equal to this if delta t is very, very, very small. Well, so then you say, okay, what happens to this thing if I make each interval very, very small? Or in other words, if I make the number of time slices go to infinity. So you can write it like this, some people write it like that. It's of course the same thing. Okay, you either make the length of each time slice go to 0 or you make the number of segments go to infinity, is the same thing. Okay. This thing then, of course, laziness is also given then a shorthand notation. Okay. So what people do is that, well, उन्होंने कहा ये छोड़ो, n और j is equal to 1 को गोली मारो, इसका डंडा पकड़ो, इसको ऊपर कर लो, इसको डंडा इसको नीचे कर लो, दरमियान में इसको लंबा कर दो. So what you end up with is this, okay, which is, looks ugly, so then they made it curly. That's, for those of you who haven't realized, that's your integral sign, and integration is basically a sum. That's what integration stands for. If anybody from now on says that integration is an area or integration is the reverse of differentiation, go to the 4th floor and jump out of the window, okay? So integration is a sum. And people have known this, not exactly in this form of course, but very close to it for thousands of years. Anytime you want to deal with a problem dealing with curve, the only way people knew how to deal with that was to chop up the curve into small straight lines. Okay, and then they said, well, if you are making each interval going to 0, then you are basically looking at the value of the function at every point. Okay, so then this j disappears essentially because you're looking at the value of the function at every point. So you just write f v of t And this delta t, of course, in the limit becomes dt. From the initial time to the final time. That is your distance, total distance traveled. Okay? But of course, ये ठीक है, ये तो कर लिया, बड़ा impress भी आप लोगों को कर लिया. There's one big problem, which is, no, there's a much bigger problem. सही मैंने आपको उल्लू बनाया है, वो सही जिस तरह वो सही स्कूल ऑफ बिजनेस वाली प्रेजेंटेशन दी आज है. ये तो ठीक है, there's all kinds of fancy language, fancy symbols and all that, but how in the world do I actually calculate this thing? ये तो मैंने बात ही नहीं की अभी कि how do I at the end of the day, how do I get a number out of this? How do I deal with this elongated s? You can't set up this sum. So remember, 600 years ago, if somebody asked somebody कि भाई ये distance, find out the distance on the speed, and the speed keeps on changing. That's literally what they had to do without a calculator. They had to chop up the time into small pieces, essentially calculate the products of lots of numbers and add up all those numbers, and of course there was a very high chance of making some mistake along the way. It was an extremely painful, laborious process. जो आपका एरिया वाला प्रॉब्लम है, that's basically exactly the same thing. That's why area जो प्रॉब्लम है, that is so important. It's not actually finding out the area. वो कोई जमीन वगैरह की लड़ाई नहीं थी. It was actually that once you can solve that problem, you can solve many other problems straight away. For example, this problem. Okay. Well, how you do this? The answer is provided by something called by देखो कितने, you know, mathematicians are very modest people, so they gave it the very modest name of the Fundamental Theorem of Calculus. Okay. क्या हुआ है? पता नहीं क्या कह रहे हो हैं? Oh, okay. Oh, okay. So what this says is, I won't be proving this, of course. In the readings you can see a rough proof. It's not really a mathematical proof, but it's a rough motivation. How you calculate it is, exactly, yes. So if you're dealing with this, in general, if you're dealing with this, the way to calculate this is that. So you essentially, if you're going to do this sum, find out first of all an antiderivative of f, calculate the antiderivative at a, calculate it at b, take the difference. Okay. One very quick way to see this is, suppose I have to do this. Ti. Okay. If you just do it like that, what is this thing going to be? You are taking the ratio of a small change in x with a small change in time, and then you are multiplying with a small change in time. So you are going to add up over small changes in x, kind of ये चीज काटी जाएगी, so you just have addition over small changes in x. So what do you get then? Total change in x. If you add up over small changes in something, what do you get? You get the total change in that quantity. Okay, so that's it. Yeah, I know. Roughly speaking, I'm not being very mathematically rigorous. Okay, like I said. Okay. Okay. In your recitation tomorrow, hopefully, we don't remember 1965, so you will have a recitation tomorrow. If you do remember it, too bad, okay. So in your recitation tomorrow, you'll see more details of that. Okay. Okay. Now let's apply this Okay, so you have v is equal to dx by dt. Let me write it another way. You have dx. Very often in physics we write this. Yes, mathematically, not very rigorous, but it works in physics, so it's fine. You can rearrange this into this. What is this thing telling you? This thing is telling you that if you chop up, this is the way that you read this. If you chop up your time interval into small pieces, small slices, for any slice, the change in position equals the velocity for that time slice times the time interval. That's what this equation is telling you. To get the total change in position, you can just add up both sides. The sum of small changes in x would be या जब सीढ़ियां चढ़ के जाते हो, your height change keeps on changing by a small amount. At the end of the day, what's your total change in height? तो अस्तगफिरुल्लाह, सीढ़ियों के ऊपर गए हो, वापस नीचे नहीं गिर रहा है. You climb a set of stairs, you go to the top floor. Your total change in height is nothing but the height of the top floor. That is the sum of the heights of each stair. You add up small changes in x, you get the total change in x. Another way to see that is, अगर मैं वो j वाली की बात करूं, x1 minus x0 plus x2 minus x1 plus x3 minus x2, इस किस्म की चीजें हो रही होंगी जब मैं इसको ऐड करूंगा. And what's going on then? You have x1, देखो x1 कट गया है, x2 कट गया है, all terms will cancel other than the first and last term, and that's the total change. Okay, so there are many different ways to see it. Okay, but of course एक तरीका है जो आपको उसी वक्त आ जाएगा. ये सारे सिंपल तरीके नहीं आपको समझ आए होंगे. If you are adding up both sides of this equation, what are you doing? You are integrating. Okay, this you are adding up from the initial position to the final position. What do we mean by the final position? Well, let the final position be arbitrary. It's the position at some time t. Let's just call it x. Okay, right? And we have to add this up from, because you have chopped it up into time slices, from the initial time, which let's take that to be 0, to the final time, which is some time t. Okay, so you essentially have this, and now you're adding up both sides from some point to some point, and that's what you're going to get. Okay, okay, now there's a problem over here. Shh. क्या problem है? The symbols का problem है. You're using one symbol for two different things. Well, you're actually using two different symbols for two different things. X का देखो इधर d है, ये वाला x कौन सा x है? You are moved from time 0 to time t. इसको आपने slices की हैं. For any one slice, this is true. This is the distance moved for any one of these slices. ये जो इधर इस टाइम पे जो distance है वो है उसका x. These distances that you are adding over are the intermediate distances. This x is not the final x over here. These are the values of the position between the initial position and the position at time t. तो ये कोई और x है, ये वो वाला x नहीं है. This is not the same x. So you have to use a different symbol over here. So again, height of laziness, people just put an apostrophe on top to denote that this x with a prime shows that these are the intermediate values of x, not the final value of x. Okay. Of course, अगर आप इधर xf लिखते, then this is fine. Okay, but just be clear that do not confuse this thing with this thing. Okay. And same problem over here. These are essentially these t's are intermediate values of time t. This is your final value of time t. So put a prime over. Okay. अब आप सब कुछ कर सकते हो. ये देखो ये इधर 1 है असल में. इस ये इंटीग्रेट करोगे तो क्या आएगा? ये अब आपका ए लेवल वाला काम आता है सारा जो आपने किया था। ए लेवल में लिटरली आप जो है वो गाय आखिर में खरीदते हो, गाय बल्कि खरीदते नहीं हो, भूसा खरीद के आ जाते हो क्या? ओके, सो एनीवे, सो यू हैव दिस थिंग नाउ इंटीग्रेटेड। ये इंटीग्रल सिर्फ आपको ये दिया जाए। ए लेवल पता नहीं पेपर 3 या पेपर 4 जो भी है, एक तो लीक भी हो गया था इस दफा, तो जो भी है ये क्वेश्चन दिया जाए, व्हाट विल यू आंसर? तो इसका एंटी डेरिवेटिव आप निकालोगे, आप कहोगे वेल दिस इज एक्स प्राइम, क्योंकि एक्स प्राइम को मैं डिफरेंशिएट करूं विद रिस्पेक्ट टू एक्स प्राइम, आई विल गेट 1 एंड देन आई पुट इन द लिमिट्स एक्स नॉट एंड एक्स, और ये फिर क्या आएगा? x minus x naught, right? So the left hand side is x minus x naught, but you should have been able to write that down straight away. This is the sum of the total of the small changes in x. क्या आएगा वो? Total change in x minus x naught. If you know what you are doing, many times you can straight away write down the answer very quickly. This is equal to 0 to t v dt प्राइम। ये अब आपने ए लेवल में इंटरप्रेट किया होगा, दिस इज द एरिया अंडर द वेलोसिटी टाइम ग्राफ। सो द चेंज इन पोजीशन इक्वल्स द एरिया अंडर द वेलोसिटी टाइम ग्राफ। ओके, और अनदर वे, इफ यू नो दिस फंक्शन v, देन यू कैन डू दिस इंटीग्रल। इफ v इज कांस्टेंट, क्या आएगा ये आपके पास? v बाहर गया इंटीग्रल के 0 to t dt प्राइम, ये इंटीग्रल किसके बराबर होगा? t, that's it, t minus 0 which is just t. So you get x minus x naught is equal to vt, same thing as before of course, but now done using sums rather than thinking about antiderivatives. Anti-differentiation and integration, aka sums, are essentially the same thing, even though they look very different to begin with. Okay, so this idea of setting up a sum and then calculating this sum using integration is something that you'll see over and over and over in this course. Okay, आपको ये मैं नहीं इंटरेस्टेड दूंगा कि x स्क्वायर मल्टीप्लाई बाय e रेज़ टू पावर x को इंटीग्रेट करो, मैं ये इंटरेस्टेड दूंगा कि why should I even bother to integrate that? Okay, unfortunately वही काम आपको नहीं आता होगा. Okay, so tomorrow recitations, lots of questions related to this, and then of course next week we'll do some more.